Hello, welcome back to differential equations. And this is going to be the first of a few shorter videos to talk about the main idea behind these methods called the methods of Laplace transform. This is in chapter 7. And we are going to start by reviewing the big idea that we talked about on Thursday, which is every time you look at the transform methods, you are looking at the methods which look at the problems that we wanted to solve, but instead of solving it, we transform it to another area, solve it over here, and then find a way to inverse it back so that we can get the solutions to the actual questions that we wanted to solve. So usually these are very powerful methods because we can directly bypass the questions that we wanted to solve and instead solve another problem which doesn't look like it is a type of problem in differential equations, and then find a way to convert that information back to the solution of a differential equation. So you will see in at the end of all this material that the idea is to take differential equations, right? So differential equations, when you want to solve it, there's a questions in calculus, right? So you have derivative, antiderivative, that sort of stuff. But after we transform it using the Laplace transform, the problems that you solve is algebra problems. So it has nothing to do with derivatives, nothing to do with integral. It's just basically partial fractions type of computations. And then after that, you can invert it back and you get the solution of a differential equation. So that's the main idea that we talk about on Thursday. So this first videos here is going to be a very quick review of the material that we already studied on Thursday. So there's only a few things that we have to make up for the class that I missed on Tuesday. So that actually we are not too far behind. So that's kind of like good news. And so I wanted to kind of like repeat, not the whole thing, of course, but the main idea of the things that we talk about on Thursday, and that will be basically the first videos. Okay, so the things that we talk about on Thursday, we started with these definitions. At first, you kind of see that it's kind of weird. That why do we define it this way? So the reason why we define it this way is because it turns out it's going to be very useful. Okay, and you can see actually when you finish all these videos, you will see that how the entire scheme is being carried out. Okay, how do we make this thing happen? Okay, so and this all started with this definition. So the definition tells you if you are given a function ft, how do you transform it to a function in S? So the original input function is going to be a function of t, and the output function is going to be a function of S. All right, so not to go over too much of this, but just to highlight the things that we did on Thursday. We started with the easiest example, which is looking at the constant value functions, which is ft equal to 1. Don't look at this notation as if it is a Laplace transform of a number. Laplace transform act on functions. The input of that transformation is a function, not a number. So even though you see something like this is understood to be a constant value function. And then we saw on Thursday how do we use the definitions of the Laplace transform and compute all this integral. The definitions of Laplace transform is given by in improper integral like this, and then after the computations you see that we got 1 over s. So that's the input, Laplace transform of a constant value functions. Usually nobody write like this because it's too much. So usually the shorthand notation is just like this. And after that, you see that this is the output, right? So the input functions is a function of t. The output function is a function of s. So that's one of the example we did on Thursday. The second example that we did on Thursday using the definition itself is showing you that the Laplace transform of exponential function is this. Okay, and the rest of it I didn't do it because you can look at from the notes in the exam. Usually we basically never really ask you to do this kind of derivation. So we just want you to know that Laplace transform for a function t, for example, if you go through these computations, it turns out to be 1 over s squared. So this, if you are interested, you are mathematically inclined, and you wanted to know how actually this is all done, you can look at the notes. Same with the Laplace transform of sine functions, cosine functions. Computation a little bit more complicated because it involves integration by part. And but you should be able to go through all this if you like this sort of stuff and you still remember all your calc too. But the main thing is that there's several main thing. Okay, so let me point to you here. So the main thing is that now we know, of going through all those definitions, this is the result of the Laplace transform of all this function in t. So that's what we did. This is the result that we have. And then we also mentioned that Laplace transform is linear, which means right here, that's the meaning of being linear. Okay, so because Laplace transform is basically an integral. In fact, it's a good idea to think about Laplace transform as an integral, so the manipulations kind of reminds you like, okay, there's the kind of manipulations that you saw before using the integral method, because they're basically integrations. And so that's what we did. One of the main idea is that at the end, you need to know this table. This table is also going to be provided in the exam. Okay, so that's the first part of what we talk about on Thursday. And then the another main part of it is looking at inverse, right? So I don't want to go through all this thing. I'm going to kind of quickly show you this thing over here. So this thing over here, sorry, this thing here. So this is the part where we're looking at the definitions of Laplace transform. We compute it, we got all this stuff. You do need to know how to read this table. And then we talk about the inverse, right? So if you have a function ft, right, you transform it to here. Now it's a function of s, and also there's the notations. The standard notations for Laplace transform of a lowercase f is uppercase f. Sorry, the Laplace transform of a lowercase f is going to be uppercase f. This is a function of t, this is a function of s. You can see here, like this. And then we wanted to be able to come back. And coming back is what we call the inverse transform, which basically you just need to read this thing back, right? So the inverse transform of something like this is 1. Inverse transform of something like this is this. So this table is actually not going to be provided in the exam because it's basically coming from here. You just read it backward, you just read it backward, you just read it backward. So if you see something like this, inverse transform it, you're back to the function of t. Saw this, inverse transform it, you get a function of t, and so on. So that's what we did. In fact, on Thursday, you'll see that the inverse transform is a little bit more complicated because things doesn't line up perfectly like this, and we spend quite some time to make sure that you know how to do the manipulations on how to actually compute the inverse transform. Also, another big things to know is that both Laplace transform and the inverse transform, they're all linear. Okay, so they're all linear. Again, think of it like a type of integral. So for example, if you are doing something like this, let's say this is 1 over s cubed, s to the power 4. So you can put a 3 here. All right, you can put a 3 here, 3 factorial here, s to the power 4. And then you divide it by 1 over 3 factorial. And this 1 over 3 factorial can be taken out, okay, because of the linear property. So that's what we have on Thursday.